faccio Roma è inutile qui, col grandangolo praticamente è ancora meglio.
Allora, so yesterday some of you made the interesting observation that in a reader-writer implementation like this one that we are showing, there are some potential delay inside execution of the writer. So it can definitely happen that reader comes, execute, and another reader comes, execute another reader, and so on, and the writer never has the lock on it. So that was the case even with just two readers. So if one comes and the other one waits here, so the one go on, here performs a post, the one pending here continues, this continues, and so on. Okay, with just two readers, they can ping-pong the access to the shared synchronization semaphore. Okay, and this causes the writer never been able to get to execute. Okay, so this is something unfortunate. This is something we would like to avoid in some cases, to avoid the writer starvation. What if we have more than one? We want to implement, an application with more than one pending writer. Meglio? No? So what we have more than one pending writer, so we would like to accommodate some different mechanism to allow writer to execute. Let's see what did we change here. So here more or less is the same before. So get back here. Okay, this was the previous implementation. Okay, and this is a current implementation. You may notice that it's the same, right? So we have same wait and same post, same wait and same post, and then synchronization primitive here, and the synchronization posting here, right? The reader is absolutely like it was before. Okay? You remember here, number of readers that enter the section ++. If I'm the first one, then I take the synchronization semaphore, okay, preventing any writer to execute. If not, I just continue, and then I post and release this mutex here. I read the buffer. While exiting the critical section, what do? I take the lock on the reading semaphore, I decrease the number of readers. It's a shared variable, so it should be protected within critical section. If I'm the last one, then I'm the one that posts the writer to continue executing and releasing the reading units. Okay? This is exactly as before. Here, what changed? Before it was like this. Okay? Just a very simple protection of the critical section with the synchronization mutex. Here I made it a little bit more complex. So now we have a preamble and a post phases here, while the writing side is protected by a different mutex. Okay, so I'm adding a mutex there as well, binary semaphore, that protects here among multiple writers trying to access the writing section. Let's go step by step. What do we have here? So here we have another semaphore. This is a private semaphore to the writer. This is a private semaphore to the reader. Okay, this we had before. This one is new. Okay, so here we have the case where we may have multiple writers trying to attempt writing the buffer. You remember the specification we had? We can only allow one writer at a time in writing, while we can allow multiple readers simultaneously reading. So here I have this writing lock, okay, protected, and the same here. What do I take into account here? I keep track of the number of writers that enter this section, okay, the number of writers that enter this section okay, plus plus. So if I'm the first one, here, something new, I take the sync. So I would like to be the one that avoids anyone else to start messing up with me. Okay, so I'm the first one. Here, I protect the writing section with a mutex, so that no one of the writer will come to interfere with me. Let me repeat. So here I keep track of the writers that were allowed to enter here. Okay, so I just allow them to enter freely. Okay, as soon as a writer, maybe I have writer locked here, but I allow new writer to come. Okay, this is the basic difference with the first implementation. Okay, in the previous implementation, a writer can never enter the critical section. You remember? So if I had writer arriving here, all of them block. Instead here, I keep track the number of writers that enter. A writer is always allowed to enter. Okay, is always allowed to at least try to enter. Okay, as long as this mutex, the private semaphore of the writer is available, but it's released in this short critical section, the writer is registered, so increasing the number of pending writers, while in the previous case we didn't keep track of any number of pending writers. Okay, here we keep track of the number of pending writers. If and only if I'm the first one, then I take the synchronization lock. Okay, only if I'm the first one, I take the synchronization lock. Then, since multiple writers can be here, right? They just release the post, the semaphore, and they can continue. I need to insert this mutex. If I don't insert this mutex, then I may allow contention on the writing section. Okay? So I need to insert this mutex here to protect the writing section among multiple writing attempts. Okay? What do I do at release time? When I exit the writing critical section, I of course decrease the number of pending writers. If and only if I'm the last one, I release the synchronization semaphore. Okay? Only the last one releases the synchronization semaphore. So in this case, if multiple writers arrive, okay, assume like the first one arrives, this goes to 1, and this gets the sync, okay? Then the second one arrives while the first one did not yet finish, okay? It is allowed to start. I have this number in 2, so I will not perform this operation, otherwise this would have been failed, right? Let me repeat. First writer comes, and W becomes 1, okay, from 0 to 1. So the first one takes this synchronization lock. The second one that arrives puts this to 2, so it doesn't perform this weight. Otherwise, it would have been blocked. It would have blocked on that way. But NW is 2, and this was 1. Are you following me? Okay, it's a little bit tricky, but you need to understand it, okay? And I post the writing semaphore. If a third one arrives, it becomes 3, 4, 5. So if I have 5 writers that are pending here, I need to protect the writing session with a mutex. Okay? So that only one of them at a time will be able to pass this section, to execute atomically this writing section. Okay? Then, at release time, not all the writers release the synchronization semaphore. Only the last one, okay? In that way, I give privilege to the writers instead of the readers, right? So if I have here 5 pending writers, I will not release the synchronization semaphore, okay? I will release it only if I'm the last writer pending, okay? It's a little bit complicated, maybe at first sight, but it's nothing difficult. with the same scheme that we used here, we replied it here. Okay? Now it's a little bit more balanced situation. So if I have multiple readers coming and coming and coming, no writer will ever be executed. But this time, when I have multiple writers, I will impose the same effect on the reader. So a writer can keep coming and coming and coming without the reader to execute. So it's a little bit fairer than it was before. Okay? Still, it is not fair. It is not a FIFO synchronization. It doesn't implement any first in, first out policy. Okay? We need something more to implement a fairer policy. So, summary, starvation. A reader is blocked for a finite time. The writer suffers starvation. If we have two readers and one writer, we said it before, so while so R1 and R2 can just ping pong each other, okay, never releasing the synchronization semaphore, right? This we said before. So a potential solution is reader should not be counted whenever there is a writer waiting for them. This is an attempt to avoid writer starvation. Again, do not count readers whenever there is a pending writer. Okay? This makes it even more complex, the implementation. Okay? Even more complex. I highlighted here what I changed with respect to the previous solution. Okay? So I added a further synchronization. These are just examples, okay? Then we will use something different. But it's just example to let you understand a little bit more about the dynamics of semaphore and synchronization. So I added here a synchronization and a synchronization. So sync one, okay? A wait and a post. And here, what I have is the sync one instead of the sync that I had before, okay? Now this is a sync one instead of the sync plane that I had before, okay? Previously, I didn't have these, and the sync was the same as the sync here, okay? So this implementation changes the thing a little bit. So I will not count, I will not allow readers to come whenever there is a pending writer. Let's see together whether this is true, okay? So a reader can come if he is alone, he takes this lock, he takes the reading block, he enters, he takes also this lock, okay? So he has the sync one, the SR, and the synchronization semaphore, okay? Then he releases the reading semaphore and the sync one, okay? If another reader comes, the same, okay? He can enter, he will just not take this sync here because he's not the first one, okay? It is more or less as before, right? Now, before a third reader arrives, there is a writer arriving, okay? Can a writer arrive? Yes, if it comes. If this semaphore, which is a brighter semaphore, not held by the reader, it is a brighter semaphore and is available, okay? It is available, it's initialized to 1, so it can enter, a new writer is registered, okay? If it is the first one, it tries to take this lock. But who owns this sync one? The reader, right? Okay, the reader owns it. Okay? So until the reader does not release this, he cannot take it. So when the reader releases this, then this can take it. Okay? Then this can take it. And after he took it, no further reader can take it. Okay? So let me repeat. If the writer is ever allowed to take this sync, so there is at least one pending writer, if there is one pending writer, so a writer which is here, okay, a writer that took this semaphore, no further reader can enter the critical section. Okay? Again, let me repeat it a third time. In this paradigm, in this implementation, I implemented a paradigm that gives priority to writer with respect to reader. Whenever there is a pending writer, I will not allow new reader to be registered. Okay? I did it this way, so whenever a writer is allowed to enter, okay, this is done for the first one, no further reader can enter this. Okay, so they will be blocked here. They will block here. Okay? So, what comes next? Of course, I need to then signal. So remember, every time you block something, you need to signal it. Okay? So the last writer, if I'm the last writer, I will release this semaphore. Okay? Now new readers are allowed to come. Okay? But in order to solve writer starvation, now I post reader starvation, right? So if multiple writers come, then no reader will ever execute. Do you agree with me? Okay? So here, it is failure from a writer point of view, because even if 100 readers arrive, I will respect the arriving moment, the arriving time of the writer. Okay? So if this writer arrives after 5 readers, and then 100 readers arrives after that, this writer will be served at 6th position. Okay? So the remaining one will not delay further the writer. But the other way is not true. So if writers keep arriving, okay, I will never reach this situation until all of them are served. So a reader is definitely starved. Okay? So just to tell you that you have this tricky problem, even in a very simple setting that you can imagine. So reader writer is a very simple example, right? How many times it may happen to write in a shared buffer and to read from a shared buffer? This is probably the simplest kind of synchronization, and you understand how difficult it is. You know, at first sight, it seems so complex, right? So this kind of synchronization, I need to make sure that I don't have any deadlock, that I don't forget to, I didn't forget to wake some of the pending threads up, you know? So we have 1, 2, 3, 4, it's better to count that, 1, 2, 3, 4 semaphores, right? 4 semaphore and 2 counting variables, just for a simple reading writing problem, and still we did not solve the reading starvation problem. Okay? So it seems a bit complex. I will teach you how to make a better use of semaphore to avoid this kind of problems. Okay? So here, as I just said, there is a starvation for the readers. Can we solve the problem in a more general way without relying on this heuristic that I always adjust, adding a further semaphore and a further semaphore, which is what I did when I was in your position, you know? So the first attempts I did in solving synchronization problem is just adding semaphores, you know? Adding semaphores. And whenever I realized that something in the synchronization was not taken proper care of, I was just adding further semaphore and so on, you know? So you end up using 100 semaphore and you still don't have what you need, okay? So I'm trying to teach you later a better use, a smarter use of semaphores that will allow to implement smarter policies to wake blocked tasks up in a proper order. Okay? So if I would like to maintain a first in, first out ordering with requests, so if at least I would like to implement something that if at least one writer is blocked, every next reader blocks. And the other way around, I would also like to implement that if at least one reader is blocked, every next writer blocks. Okay? I would like to implement a fair strategy of this kind. So in order to do that, we use private semaphores. Okay? Private semaphores. This is something that I teach also to your colleague of parallel computing, because it's needed when you have a concurrent system based on multiple cores. Okay? So whenever you would like to properly synchronize concurrent instances, private semaphore are a good tool to use. So what are private semaphore for? So I use a private semaphore every time I would like to specify the policy to wake up, block, thread, or processes. Okay? I would like to specify a peculiar policy to the application setting, the problems I would like to solve, specifying the way in which, or in this case, readers or writers are waked up. Okay? So avoid starvation of both reader and writers, and whenever a resource becomes free and more than one process is blocked, so if I have multiple processes, I would like to activate them according to a particular policy. Okay? So, in general, when we use a shared resource, when we share a resource in our system, we block because some kind of test fails. Okay? For instance, a process inserts an element. You remember the case of circular buffer. When the buffer was full, one of the implementation we saw had the inserting task, the producer task, blocking because the queue was full, right? So that was like a test that we did. If number of items is 10, then block. Or if private semaphore full was 0, then block. Okay? So when this process blocks, it blocks on a private semaphore. A private semaphore is a semaphore that is only used by that thread itself and only. Better than that thread itself, by that group of threads representing the same tasks. So in the producer-consumer, we had a full semaphore and an empty semaphore. Okay? One was more useful for producer, the other one was more useful for consumer. Okay? So if you remember, the producer blocked on the full semaphore. The consumer blocked on the empty semaphore. You remember that, right? So these are private semaphore in the sense that only one of the threads can block on that semaphore, not both. Okay? The empty thread will signal the other producer to unblock from a full semaphore, while the producer will signal the other consumer to unblock from an empty semaphore. But still, the blocking, the wait operation are privately performed only by one of the tasks. More than one of the tasks, I said, is a group of tasks. So I can have multiple producers and they block on the same semaphore. Okay? Multiple consumers and they block on the same semaphore. So this is a private semaphore. Again, a private semaphore is a semaphore which is used only by one thread or by a class of threads. For instance, the class of producers, okay, or the class of consumers, or the class of readers, or the class of writers. Okay, multiple instances of that class of processes. There are two ways for using a private semaphore. I'm sorry to have this heavy class very late in the afternoon. This is quite heavy, I know, but okay, try to pay a little bit of attention. Maybe we will finish up a little bit earlier today for your convenience, okay? So, try to follow me, because we have two solutions that should be really printed in your mind in order to be able to solve the exercises and examples that we will also do in the written, in part of the written example, okay? So these are solutions for implementing private semaphore. We will see first solution and then a second solution. Okay, so a first solution, I have one mutex that I typically use in the classic way. Okay, you see some wait and some post, and this is the critical section protected. Okay? Then, one wait and one post. This is checking a condition to eventually block, and this is later changing the blocking condition. So typically, this preamble is executed before the critical section, and this thing is executed after when waiting up. Okay? So, let's check it. So, we have one mutex, I said, used in the preamble here and here, wait and post, and in the release, here and here. Okay? Mutex. Here. And then we have a set, can be 1, can be 100 of private semaphores. These are semaphores, again, which are exclusively used by one process or a class of processes only. Okay? Then I initialize the mutexes to 1, the only mutex to 1, and I initialize the private semaphore to 0. Okay? Private semaphore are initialized to 0. Okay? Let's see what happens here. Okay? If a particular condition is satisfied, so if this task is allowed to enter what is here, okay, after this preamble, this task is allowed to enter the critical section. For instance, if the queue is not empty, or if the queue is full, or if there is one pending writer, or if there is no pending reader, whatever condition you would like to implement, it varies from problem to problem, right? It depends on the problem you're trying to solve. So here you implement the condition to control, okay? If this task is allowed to enter the critical section, then what do? You register that you allocated the resource to that task. For instance, you can increment the counter. If it was a reader, number of reader plus plus. If it was a writer, number of writer plus plus. So I keep track, I register the thing that this task was able to enter. Okay? Number of tasks of that class plus plus. Okay? This is the typical way we keep track of the resource allocation to I, to that process I. Then what I do here, something strange. I do a post of a semaphore that I never tried to acquire. I do a preventive post. I do a preventive post of something that I will wait here. Okay, this is kind of a strange mechanism. Okay, this is kind of a strange mechanism the first time. So I do a preventive post for something that will be tentatively locked here. Okay, what is this post for? So I said if the condition is met, so I will be allowed to enter the critical section. So I do a previous post so that when I will perform the wait, I will be able to enter. Okay? So you remember, what does the post do? The post does a +1 on the semaphore. If the semaphore is 0, now the semaphore is 1. Okay? So this is the else part. This is the after part. So I will release the mutex and I will be able to enter, okay, this critical section. Okay? I will repeat this part, okay? So, if a condition is met, I register that I was able to enter, so number of reader plus plus, number of writer plus plus, whatsoever, who am I, okay? I preventively perform a semaphore post on the private semaphore, which was initialized to 0, so that when I will try to take it, I will be able to do that, and I will be allowed to continue. Okay? The other way around, what if the condition is not met? Okay? What if there is a pending writer, so I'm not supposed to enter the critical section, for instance? Okay? What happens? Then the bracket ends here, so I execute the else here. So else says, recorded I is suspended. So I will keep track, not that the number of reader increases by 1, but that the number of blocked reader increases by 1. Or if I'm a writer, that the number of blocked writer increases by 1. Okay? So here I kept track that I was able to enter, so the number of reader, if I was a reader, plus plus. Here I will record that the number of blocked reader increases by 1. Okay? And I don't do anything else. I will not perform a post, so that I will first release a mutex, and I will block here. I will block here, okay? Because I did not perform a post, that semaphore is 0. I will try a wait here, but the semaphore is 0, so I blocked. Okay? Remember, whenever someone is blocked, there should be always someone that wakes him up. Okay? Who shall wake me up? Let's see what is executed at the end, typically at the end of the critical section, which is this. Okay? So this is like changing the blocking condition. This is like what you typically perform while exiting a critical section with private semaphore to wake up threads that are blocked on a well-defined private semaphore. Okay? If Windows starts bugging me. Okay. So the part to release when I'm blocking. So again, there is a wait and a post, a clean wait and post of the mutex. Okay, just protecting the critical section. Then I release the resource. What does it mean release the resource? It's better record that you released the resource. So if here you incremented a counter, here you decrement that counter. Okay? If here it was NR plus plus, here is NR minus minus. Okay? Then I'm done. Then I'm done, for me, according to me. But I need to wake potentially someone up. Okay? So when I need to wake someone up? If wake up someone, so for instance, if the number of suspended tasks is greater than 1, you remember that first we kept track of number of blocked reader or number of blocked writer. So I can state here, if there is someone to wake up, so if there is a pending blocked reader, okay, then try to wake him up. Okay? I, for instance, is the process to wake up. So I can selectively wake up whoever I want. Do I want to wake up a reader? Then this I will be the index of a reader. Do I want to wake up a writer? Then this I will be the index of a writer. Do I want to wake up a process 122? Then I will be the index of process 122. Okay? I can selectively decide who to wake up. So which class of process to wake up, better to say. Okay? If I have 100 different classes, I will have 100 different private semaphores. I can select which one of these classes to wake up. Okay? If I have just 2 classes, reader and writer, I will decide to wake up one of the reader, not which particular reader, because I have just the whole class of readers, so I will not be able to choose which one of the readers. If I wanted to choose which one of the reader, I should have assigned a different private semaphore to each of the reader. Is that clear? Okay? This is the basic philosophical meaning of the private semaphore. Okay? They allow you a perspective on who to wake up. If you just divide into classes, then you will be able to say which class to wake up. If you assign individual semaphore to each of the process, then you will be able to pinpointing which of the semaphore to wake up. Okay? So this is here. So select which process to wake up. Then register that you wake that process up. It's your task here. This is the corresponding line of here. Why am I doing it here? Why am I incrementing the number, for instance, of the reader that entered the section here? Because the blocked reader was never able to execute this part. The blocked reader went directly to the else part. So no one kept track of the resource allocation was to be given to that blocked reader. Okay? I will repeat it later. Okay? Then record that that process is no more suspended. What does that mean? You remember what happened for the suspended project? That I recorded that it was suspended, so I increased by 1 the number of blocked process of that class. Number of blocked reader plus plus, we set here, okay? Here I will perform number of blocked reader minus minus. It should be always consistent. This, here I don't have counters, but typically you have counters, okay? These counters should be consistent, always. If you are registering the number of readers entering the session, it should be consistent. If you register the number of block tasks, it should be consistent, okay? These operations here are the ones that maintain consistency along the counters that you're using, okay, to monitor your application. And then, this is really the post. This is really the posting action. So this is really when you wake one of these guys, for instance, up. Okay, the one that was waiting on the private semaphore is waking up here. Okay? Note that this index may be different from the index of the tasks that calls it. Okay? This may be task 1, and here is a private semaphore of task 255. Okay? So they should not be corresponding. Okay? This is typically, if I'm task 1, this is the private semaphore of task 1. But when waking up, I can wake up task 125. Okay? So this is a private semaphore with which I wake up someone else. Remember with the case we saw, producers and consumers, right? So we have the full semaphore, which was private, of the producer. The producer only could block on that full semaphore, okay? It was like this, okay? While it was the empty, it was the consumer that performed the post on the full, okay? So the producer had a wait on the full and a post on the empty, while the consumer has a wait on the empty and a post on the full, okay? So these may be different to the task index of the task private semaphore that is executing that. And then, of course, remember always to release the mutants. Okay? Remember always to release the mutants. Okay, let me repeat this again, just to fix these things in your mind. So this code is performed while exiting the critical section. So it's protected by a mutex, okay? Mutex wait, mutex signal, okay? So I release the resource, meaning I decrement the counter that I incremented here, okay? When I enter that critical section, I just decrease it here. The rest that follows does not concern me, but it's me waking someone else up, okay? So I'm registering already here, okay? Now I would like to wake up someone else, and I will keep track on that someone else counters, okay? So if I wake up task 35, then I will increment the number of processes kind 35 which are entering the critical section. So if that was like the number of readers plus plus, okay? And record that the number of blocked reader decreased by 1, okay? So if that was waking up a reader, this should be NR plus plus and BR minus minus, okay? This keeps consistencies on the counters that keep track, if they are counters, that they could be Boolean or logic variables or whatsoever, okay? Typically these are counters, okay? These instructions maintain consistencies of the counter that monitor the number of blocked processes or the number of processes that enter the critical section. Okay? Then I wake them up, okay? I wake them up and I release the mutex. Okay? I wake them up and I release the mutex. Okay? Question?
In condition, an example of condition?
If, like in the previous slide, what we saw, do not wake up, do not allow a reader to enter when there is a pending writer, right? Okay. So in that case, the condition would be if number of blocked writer is 0, okay, so there is no pending writer, then I'm allowed to enter, okay? If instead the number of blocked writer is greater than 0, so there is at least one pending writer, I will block here. It will be a responsibility of the writer to perform this kind of chunk of code to wake me up here. Shall I repeat?
No, I understand this part. And with the resource allocation to if.
Okay, so if number of blocked reader is 0, I'm allowed to enter, and I'm a reader, okay? So if the number of blocked writer is 0, the reader is allowed to enter, Okay? So here, I'm a reader. I was allowed to enter number of reader plus plus. Okay? Number of reader plus plus. Send post to the private reader. Okay? This I don't execute. Release the mutex and post and await, which was previously allowed here. So I enter this thing. If instead, what happens if this was in the condition there was a pending writer? So I block, so you execute the else, number of blocked reader plus plus, number of blocked reader plus plus, release the mutex, otherwise there cannot be any progress. Always release the mutex before blocking. Always release the mutex before blocking. Never do the other way around. This is a big mistake. It is a deadlock. 99% of the time it is a deadlock. Okay? So release the mutex and block. Who will wake me up? Not a reader, probably writer. Okay? Writer will perform that. So if there is someone to wake, for instance, this could be NBR, so number of blocked reader. Is it 0 or greater than 0? If it is greater than 0, there is someone to wake up. I wake up a reader. I put number of reader plus plus, number of reader plus plus, number of blocked reader minus minus. Okay? And send post on the reader. Question for you. Isn't this putting number of reader plus plus adding 2 times to a block reader? Because I did number of reader plus plus here, and I can do number of reader plus plus here.
There is the condition wake up someone, and if I know reader block, number of blocking reader is 0, I don't enter in.
Yeah, better said. So if there is a blocked reader, that blocked reader is blocked. So it did not perform this part here. Okay, it did not increment the counter. That's why you should increment that counter on behalf of him. Okay? Questions, problems, too difficult, headaches? Okay? So note that the weight on the private semaphore, in this paradigm, in this first solution, is performed outside the mutex critical region. So here, this is the mutex region, and the weight is outside. Okay? So I will not block while holding a mutex. I will not block while holding a mutex. Again, never block while holding a mutex. Okay? Never put a synchronization primitive within a mutex unless you're 100% sure on what you're doing. Okay? Then each process, or better class of processes, blocks on a separate, class separate, private semaphore. Okay? Since each class has a private semaphore, at release time, I can choose which one to wake up. Okay? This is a very flexible mechanism that allows you to choose which one to wake up. Okay? What are the disadvantages? That first, when acquiring, so the part on the left, when acquiring, the acquiring phase, the wait is always performed, is always executed. What do I mean? That even if I shall not block, I have a post and wait part, okay? So this is like not needed in this case, but this paradigm, in order to work, you need to perform a preventive post, okay? This is somewhat of an overhead, it's a tiny overhead, but still you're performing a post and wait despite you don't need to wait. You know you don't need to wait, okay? This is a small disadvantage of this solution, okay? And also the resource allocation is done both in the acquisition and in the release. What do I mean? That registering the number of tasks that enter is done both here, which is convenient, but also here, which is not me, it's another process that should keep track on my behalf that I was allowed to enter that critical section. So we have the same operation here and here, okay? So these are two small disadvantages of this kind of implementation. Okay, if you still have a little bit of fresh mental power, I will move to the second private semaphore solution. Okay? Again, please hold on, I will finish earlier today. Okay? Try to follow me also here. So here things are a little bit different, meaning I don't have preventive private semaphore post. I don't have preventive post. You can see that's a clean wait and post. Okay, clean wait, and there is a post here. So this is more called token passing mechanism. We will show it why. Like before, mutex and private semaphore. Like before, mutex is 1, it's open, it's green, and the private semaphore are blocked. So, some wait. This is the acquisition rules. If not conditioned, so if I'm not allowed to enter, so if there is a pending writer, okay, if there is a pending writer and no reader should be allowed to acquire the resource, okay, if not conditioned, previously we had if positive condition, here we have if not condition. If I should block, what do I do if I should block? I record the type being suspended. So if I'm a reader, number of block reader plus plus. Okay? If I'm a reader, I record the type being suspended. Okay? Then, before blocking, you see, this is a send wait on the private semaphore. Okay? Why is private wait? Let me erase that. So, the private I, so if I need to be suspended, I have number of block reader plus plus. Before suspending, the wait is the suspended primitive, right? On the private semaphore, which is 0, I need to release the mutex. Before suspending, I need to release the mutex. Otherwise, deadlock always should ring a bell when you suspend. Did I release the mutex? Yes, okay. I didn't do that, then problems may arise, okay? And then I block, okay? And then I block. Whatever is after that will be executed when someone wakes me up, right? When someone wakes me up, the rest will be executed. So record that I has been woken up, okay? So number of blocked task minus minus. Okay? It's me that keep track recording whatever happens here. Okay? It's not another task. It's just me. If I'm task 3, then this is NB3 plus plus, NB3 minus minus. Okay? It's always me keeping track of the counter of the block tasks. And it's always me keeping track that I've been allowed to enter the critical section. I've been allowed to acquire the shared resource. Let me go back to this. So if I should block, then I will perform what I just said. If I instead shall not block, I simply take the resource. So number of reader plus plus and go on. If I instead need to block, I block here. Okay? Someone wakes me up, I record that I've been unblocked, so number of block minus minus. Okay, and then number of reader plus plus, and then release the mutex, and then acquire the shared resource. Okay, so this is like cleaner, simpler, if you want. That task is the only one that records the blocked, increase and decrease. No preventive post. Okay, clean wait here and clean post here. Okay. And the block, and the task blocks here. Instead, it was blocking at the end before, right? Here it blocks within here. Okay? when I'm blocking, so typically at the end of the critical section, typically, but it could be another synchronization task, it can be whoever to perform this changing a blocking condition chunk of code. So what happens in this case? This is a little bit more difficult. So this part is easier in this case, but this one is a little bit more difficult, okay? So I take the mutex, I record that I exit the critical, I release the resource. So number of reader, if I was a reader, minus, right? So I recall, I keep track that I'm exiting the shared resource. So number of active tasks on that resource minus, okay? And I'm done. Okay, now is the process of wake someone up. Okay? So if I need to wake up someone like it was before, who do I wake up like it was before? Perform a post on that private semaphore of the task that they want to wake up. Okay? Where is the mutex release? So I did a post, but I did not release the mutex because the else, the same post is not there, so I'm not releasing the mutex. Okay? It may seem an error, but it is not. We will go back later to that. Okay? So if I need to wake on someone, I don't release the mutex. I just wake the private semaphore of that task up. Okay? If instead I don't have anyone to wake up, I execute the else branch, and only in this case I release the mutex. Okay? So in this case I'm safe. So send wait on the mutex and send post on the mutex. But if I need to wake up someone, I'm not releasing the mutex. Can you guess why?
It was already released by the first block of code.
It will be a responsibility of the task that I'm waking up to release that mutex. So more or less what you're saying. So you said it was released before. Yes, the task that is waiting here, release the mutex here, okay? So when he will continue executing, I don't see here any wait on the mutex. So he may potentially execute these without mutual exclusion, which is dangerous. Let me repeat. The task that blocked here, what did it do? It released the mutex, it released it here, and then it blocked. We said you should never block while holding a mutex, right? So when he will wake up, notice that I don't see here any wait mutex. So he will potentially continue here without holding the mutex. This means that potentially 120 tasks can execute on the same shared resource, which is something we would like to avoid, right? So what I'm doing here, I'm passing the token, I'm passing the mutex from the task that wakes up someone to the woken up task. So the mutex that was was taken here is passed to the guy that wakes up here. Again, the mutex that I have here, but that if I need to wake up someone, I will not release. There is not send post, which is not in the else branch. So that mutex will be passed to the waken task, that was sleeping here. Now I'm sure that that task will continue holding that mutex. It will be his responsibility to perform the post at the end. Okay? This second paradigm is called token passing. Okay? You pass the token, passaggio del testimone, okay? You pass the token to the other blocked, to one other blocked task. Okay? So this one is easier. This one is a little bit more complicated. Okay, you should pay attention to this token passing mechanism when waking up someone. Okay? The problem is that in this solution, I cannot wake up, or it's difficult. I could, but it requires adding some code. It's difficult to wake up more than one process at the same time. So in this case, I pass the token only. I can pass the token only to one task. I cannot perform multiple posts here. So I cannot wake up 2 tasks, or 3 tasks, or 4. Why? Because I'm just passing the token of the mutex to one of the tasks. I cannot, I don't have more than one token, so I will be only able to wake up one task. Okay? I should modify the waking up code if I wanted to wake up more than one task. Okay? Typically, in the previous solution, this one was the previous. Here, it is very convenient if I had 100 readers which are blocked to wake all of them up here. So this becomes, while there is someone to wake, keep posting. So wake all of them up. Okay? All of them will be okay, right? So they will wake up here and accessing the resource. Okay? So readers, we don't care. Reader can execute concurrently while reading. So I'm allowed to wake up multiple guys. While in here, when I wake up someone, it's very loose, it's dangerous, because then they all will perform a post here, which will put my private semaphore, the mutex, in an inconsistent state. Okay, so if I were to wake up all of them, then I will encounter problems. Okay, now let's see. So this was the theoretical model. Let's see applied to the reader-writer problem. And then I will finish for today, okay? So let's see how it applies to the reader-writer problem, okay? So, I told you, we don't only use the private reader and private writer semaphore, okay, and the mutex. We also use counters. Okay, to keep track of how many tasks are blocked and how many tasks we're able to enter. Okay, so what are these ones? These are self-explaining, right? So the number of readers that were allowed to enter, the number of writers that were allowed to enter, the number of readers that were blocked, and the number of writers that were blocked. Okay, so these are the 4 counters that I use. Typically, for every class, I have one counter for taking into account who entered, and one counter for taking into account who blocked. Okay? The initialization, the mutex is 1, everything else is 0. Okay? The synchronization, private semaphore are 0, and the counter, of course, are 0. No one enters, no one is blocked. Okay? So how can I potentially implement that? Okay, let's see what I did here. Okay? Sem wait on the mutex. Okay, sem wait on the mutex. Sem post on the mutex. Okay? Sem wait on the mutex, sem post on the mutex. This is the reading action, and this is like the post and ball to wake someone else up. Then we'll see the details. For the writers, the acquisition phase, waiting mutex post, the writing path, and the waking up phase. Okay? The post phase. Okay? Let's see better. Okay. The acquisition phase for the readers. Okay, what does it do? So this is protected with a critical section of the mutex, and then I check. Is there any writer executing? Is there any writer here? Number of writers that were allowed to access the writing phase. Okay? Or is there any blocked writer? So any writer which is blocked here. Okay? Is there any writer that arrived that would like to access the resource, or is there any writer which is already writing? Okay? These are blocking conditions. In case this is true, I will block. I register that I will block. Okay? I'm registering that I will block. Okay? So this, in the example before, this is the first paradigm. Okay? I'm just changing not if the condition is true, but just if the condition is wrong, I will block. Okay? Otherwise, I can enter. Okay? So you can decide whether to put the blocking condition here or the positive condition here. Because one will go in this branch and the other one will go in the else branch. Okay? So again, if there are pending readers, pending writers or ongoing writers, I will block. Okay? I will block and I register the type block. Okay? Number of blocked reader plus plus. Okay? Instead, if I should enter, I will enter, so I will register that I will not block, I will enter, and R plus plus. And what is this? A preventive post. Okay? This is a preventive post. Okay? Here I didn't do that because I will block. Here I do a preventive block, a preventive post. Okay? So, release the mutex before potentially blocking. If I was in the else branch, I did a preventive post, I will be allowed to read. If I was in the if branch, then I will block because the semaphore is 0. Okay, we'll block here. Okay? After reading, what shall I do? Okay? It's my responsibility first to register that I will exit the section, and second, potentially to wake up someone. Okay? So first, I register that I'm exiting the section. Okay, I'm exiting the shared resource, and R minus minus. And then I check whether there is someone else to wake up. So if there are blocked writer and I'm the last reader, if there are blocked writers and I'm the last reader, I cannot wake up writer if there are still some pending reader, right? It's very important to have this, okay, as well. So only the last reader shall wake up the writers, right? And I will not wake up any writer if there are no writer to wake up, right? So if there are blocked writers and I'm the last reader, then I will wake up a writer. So one less blocked writer, one more active writer, okay? And I post him the private semaphore, okay? And I release a new text, okay? It is not the responsibility of the reader to wake up readers. Why is that?
It's a responsibility of writer.
Yes, but why a reader does not need to care about the blocked reader? Can it happen that the reader is blocked while the reader is here? No, right?
They always can.
They always can enter. While a reader is here, they always can enter. Okay? It's only writer that could be blocked while a reader is here. Okay? Okay. Okay, let's see the dual thing of writers. Okay? It's a little bit different, but it's more or less the same. So, when shall I block? When shall a writer block? Where either a reader is active or also a writer is active. So if a reader is active, I cannot write, but I cannot write even if a writer is active, otherwise the to write will leave the shared resource in an inconsistent state. Okay? So either a reader is active or the writer is active, right? Before we had instead, if a writer is active, but if a reader was active, we could allow further reader to go, right? And we checked whether a blocked writer was active. In this case, we don't need to check whether any blocked writer or reader is active. We just monitor whether there is an active reader or an active writer. Okay? This is the policies that we decided to implement. Would you like to check also whether there are blocked reader? You could. Okay? It's up to you to decide the implementation, the wake-up order that you want.
But this can happen because
we enable the writer just when the last reader finishes.
Yes, but it could happen that you are there. It could happen that. Yes, you're right. Let me think. Can it happen that a writer starts, it executes, the next writer blocks here, a reader arrives and blocks here? It may happen, right? So a reader arrives, there is a block writer, okay? There is a block, or there is a pending writer, and a reader blocks here, right? So it could potentially avoid, I don't know. Does it make sense? Let me think. So there is a block writer, and I would like to privilege the block writer instead of me. Yes, I could decide to privilege block writer when I'm there. You know, it depends on the strategy that you would like to implement. So, whenever there is a active reader or an active writer, I will block. So I will keep track that I block. So number of block writer plus plus. Otherwise, I will be allowed to enter. Okay, I'm the only writer, and there is no reader bugging me. Okay, so number of writer plus plus. This is a preventive post. Preventive post. Release the mutex and potentially block. If you had a preventive post, I don't block, I continue. If there was some reader pending or some writer pending, I block here. Okay? Okay. This is the writing part. And here it is my responsibility to do what? To recall that there is one less writer active and to wake potentially someone up. Who shall I wake up in this case? Shall I only wake up readers, or shall I also wake up potentially writers? In the reader case, it was not my responsibility to wake up readers, because we said it can never happen that the reader is blocked while the reader is reading, right? In the writer case, can it happen that the writer is blocked while a writer is active? Yes. Okay, so again, question for you guys. It is my responsibility as a writer now to wake up potentially blocked readers, but is it also my responsibility to wake up potentially blocked writer? Yes. Okay? Otherwise, they could potentially starve. Okay? They could potentially block forever if no reader comes to wake them up. Okay? So it is my responsibility to wake them up. Okay? Let's see if this is true. So my responsibility to keep track that is a writer less, to keep consistencies of the counters. Okay? If there is a blocked reader, so here I can decide whether to wake up first reader or whether to wake up first writers. Okay? I decide to wake up first readers. If there is a blocked reader, then block all of them. Okay? It's a little bit different than before, right? If there is a blocked reader, why waking only one of them up? Let's wake all of them up. They can execute concurrently, right? They can execute simultaneously. Okay? They can read simultaneously with no problem, with no consistency problem. So if there are blocked readers, as long as there will be blocked readers, so I can even avoid that, right? So as long as there are blocked readers, let's wake them up. Let's wake all of them up. So one less block, one more active post. One less block, one more active post. Until this is true, okay? As long as this is true, okay? Then, if I did not wake up anyone, so if there is no reader to wake up, then I wake up potentially a writer. So are there writer to wake up? Are there writer to wake up? If yes, one less writer blocked, one more writer active, wake him up. Only one. Do not wake up more than one. They are blocked here. If you wake up two of them, that's a consistency problem. Okay? Do not even wake up both a reader and a writer. Okay? Either you wake up any reader or one writer. Do not wake up 2 writers or 1 reader and a writer, okay? This section of code implements that. Okay? So your exam will be solving a problem of this kind. Okay? It requires a little bit of training. We will do plenty of examples. Okay? We will train to solve this kind of problems. Okay? But you will be able to solve them efficiently and properly, hopefully. Okay? And release the mutants. Okay? Note that the number of writers, if you follow me till now, cannot ever be more than 1. Okay? Either it is 0 or it is 1. I will not allow more than 1 writer to be simultaneously active. Okay? So, as promised, I will try to stop here 5:30, but promise me to come prepared Friday to go on these topics. Okay? So probably is one more, it's a quite dense class. Okay? So these concepts are very, very, very important for the written exam and to understand how to selectively wake up threads. Okay? So that's a convenient stop, and I'll see you guys Friday after you guys make sure to read these slides that I will put online. Okay? See you Friday.